Good morning. Today we are going to find out an equation or expression for the depression of a cantilever which is loaded at the free end. What is a cantilever? A cantilever is a horizontal beam with a rectangular or circular cross section which is fixed at one end and loaded at the free end. So you can see in the picture, it's a horizontal beam having one end fixed and the other end is free. And we load at the free end. So consider a beam AB in the picture of length capital L, and this beam is fixed at end A and end B is free and it is loaded with a load W. So what happens? The beam will bend and you can see the bending of the beam in the picture. So initially the free end was B. After loading the weight W, B changes to, or we can say B is depressed to the position B dash. And we are considering a section of a beam at P. Now, this section is at a distance x from the fixed end A. So, we are only considering the bending portion of the beam. So, we had considered only a small portion, a section at P, which is at a distance x from the fixed end A. Now, what is the moment of the bending couple? We had loaded the free end with weight W. So, this weight W is a force that is acting downwards. So, due to that force, there is a moment of the bending couple. And the moment of the bending couple due to W about P. We know that the moment of the couple is taken as force into that perpendicular distance. So here the force is the weight loaded, so W into the perpendicular distance to the section P. The perpendicular, we know that the entire length is L and P is at a portion X from A. So the remaining part PB is equal to L minus X. So the moment of the bending couple is W into L minus X. And after bending, the cantilever will come to an equilibrium position. So we can say that the cantilever is in equilibrium in the bend position. So there is a bending couple and opposite to this bending couple there will be a restoring couple, or we can call it as bending moment, which we had derived an expression in the last class as YIG by R. So the bending couple at P must be equal to the restoring couple or the bending moment. So when these becomes equal, we can say that the cantilever is in equilibrium. So we can equate the moment of the bending couple to the bending moment. So W into L minus X is equal to YIG by R, where Y is the Young's modulus of the material of the beam, Ig is the geometrical moment of inertia, then R is the radius of curvature. Now, what is radius of curvature? Radius, we know that B has changed to the new position. B has changed to the new position B dash, and you can see B dash as the central layer, which is called the neutral axis. So R is the radius of curvature of the neutral axis at P. Now you have to study the expression for the radius of curvature as R is equal to 1 divided by d square y by dx square. See, you had seen that the beam has bent due to the application of the load, and the depression occurs for the point B, and the new position is now B dash. So we are going to calculate this depression of the cantilever. So we had equated bending moment with the moment of the bending couple. Now the radius of curvature is given by 1 by d square y by dx square. You can see y and x in the figure. So substituting R in the above equation and rearranging, you will get an equation for d square y by dx square as W by YIG into L minus X. So you have to study that the radius of curvature is 1 by d square y by dx square. So you can substitute it in the above equation and can find out the value of d square y by dx square. We are going to find out the depression. So on integrating this equation, what we will get? We will get dy by dx, isn't it? So on integrating this equation, we will get W by YIG into Lx minus x square by 2 plus C1, where C1 is the constant of integration. So the left hand side becomes dy by dx. So on integrating, we get dy by dx is equal to W by YIG into Lx minus x square by 2 plus C1. Now we have to evaluate this constant of integration. How? We can take the condition that at x is equal to 0. At x is equal to 0 means the point A. So at x is equal to 0, what about y? Is there any depression? No. So dy by dx is also 0. So we can substitute this condition, that is at x is equal to 0, dy by dx is equal to 0. See, there won't be any depression when x is 0. So we can Substitute these conditions in the above equation and can find out the value of C1. How? By substituting x is equal to 0 and dy by dx is equal to 0. So what you will get? Do it by yourself. Then you will get C1 is equal to 0. So our equation becomes dy by dx is equal to w by yig into lx minus x square by 2. Again on integrating, what you will get? You will get the expression for integrating dy by dx. We will get the expression for y. So y is equal to w by yig into lx square by 2 minus x cube by 6 plus c2. Again another constant of integration c2. Now how we will evaluate c2? Again we can substitute the condition at x is equal to 0. Y is equal to 0, so that on substituting x is equal to 0 and y equal to 0 in the above equation, you will get C2 is equal to 0. So what is y? Y is equal to w by yig into lx square by 2 minus x cube by 6. Taking x square outside from the brackets, you can write it as wx square by 2yig into L minus x by 3. We had said that W is the load attached to the free end. Now think that I am putting a mass at the free end B. So what will be the weight? Weight will be mg. If m is the mass attached at the free end, the weight which is acting downwards is m into g. So you can substitute mg for w. So the equation will become y is equal to mgx square divided by 2yig into L minus x by 3. Now at the free end means at B. What is x? X is the entire length of the beam. That is x is equal to L at the free end B. And what will be y? Y is the depression, isn't it? You can see the y as the length, or the we can say that y as the deviation from the straight line to the bend position is as the y. So at the free end, y will become delta, where delta represents the depression. So at the free end, we can substitute x as capital L and y as delta. So substituting, we got the expression for the depression of a cantilever loaded at the free end. That is delta is equal to WL cube by 3yig, replacing W with mg, mg L cube by 3yig. Don't confuse with the letters y and delta. Y represents the depression at each point and delta represents the entire depression at the free end. So we got the expression for the depression of a cantilever which is loaded at the free end. That is delta is equal to mg L cube by 3yig. Now consider this beam to be a beam of rectangular cross section. A rectangular cross section with a breadth b and a thickness d. Then what will be ig? bd cube by 12. So substituting ig, you can get a delta for a beam of rectangular cross section as 4mg L cube by ybd cube. And if the beam is of a circular cross section with radius r, the geometrical moment of inertia is pi r raised to 4 by 4. Then delta, that is the depression, is 4 mg L cube y 3y pi r raised to 4. So here we had taken only the weight or the load suspended. Here we had neglected the weight of the cantilever or the weight of the beam. I think the derivation is clear for you. Thank you.